Today we will be talking about basically using full packet captures, if you wish, or packet captures for threat intelligence, continuous monitoring, and so on. A lot of what we will touch on today is going to be based on the upcoming SANS SEC 582 class, which is the mastering TShark packet analysis, as well as I will be touching on contents that we discussed during the SEC 503 class, which is the intrusion detection in depth class, where we talk nothing but packets, just packets all day, packets all the time. So in the 503 class, we say packets or did not happen. Basically, show me the packets. Now, if at this point you're wondering why so much emphasis on the packets, especially when maybe most organizations are placing emphasis on the logs via their SIEM, we will figure that out as we go along. But basically, as they say, or as we say in the SEC 503, the intrusion detection in depth class, show me the packets. So packets or it did not happen. Quick touch point on who am I? Currently a SANS instructor for both the SEC 503 intrusion detection in depth class, as well as the SEC 504, the hacker tools, techniques, exploit and incident handling. I am also the author, as I mentioned, of the upcoming SEC 582 mastering TShark packet analysis class, which a lot of the contents of what we will be discussing today can be found in that class. And I also blog at securitynik.com. Additionally, I'm also the author of the book Hack and Detect, as well as the upcoming Mastering TShark Network Forensics. So there is this thing called the Rootkit Paradox, because, I mean, if you take, for example, the SEC 504, we talk about rootkits in there, and we know that rootkits wants to hide. It is hiding the processes, the network connections, files, whatever it is it wants to hide. But the issue comes up with it. If it wants to hide, it must run for it to perform its nefarious or malicious activity. But similar to how we have that rootkit paradox, we can consider the same thing for almost any malware, right? And yes, you might say ransomware, we tend to know a little bit more after the fact, because now we know we've been compromised by a malware because all of our files have been encrypted. But in order for the malware or the ransomware, whatever it is, to get into that environment, it either had to trick a user to click an email link or maybe download some file. Whatever it was that caused that malicious code to get into that environment, we can detect that. Why? Because it's more than likely it occurred across the network. And if it did, it is more than likely it has left traces on the network. And if it leaves traces on the network, we can find those, or we can get better understanding of that activity, providing that we have the packets. So think about it: command and control, exfiltration, anything that the malware does that has something to do with communication on the network, we can more than likely learn about that activity. So the basic idea is all activity on the network generate packets. It's whether or not we're capturing those packets to make the most use out of it. Today's session, we will figure out some basic things we can do to grab some of those packets inexpensively and see how we can gain intelligence from that by comparing IPs, domains, URLs, and so on with data that we have in the packets. So before we get into the depths, just some quick takeaways. If we're going to talk about packets, we have to understand what is going on in the network. We cannot go about, or we should not go about capturing packets if we're not clear on how the network works to some extent. So typically when we learn about network, we learn about the OSI and the 7 layers. But in reality, we use the TCP/IP model, which has 4 layers. Whereas the OSI layer is protocol independent, which means I can probably take TCP/IP, IPX, AppleTalk, some other protocol and fit it into that model. In the case of the TCP/IP model, it is protocol dependent. And as you guessed it, the protocol in this case, TCP/IP. Now, as you notice also, the OSI has 7 layers, but TCP/IP has 4. So what has happened is the TCP/IP layer or TCP/IP model combines the session presentation layer and the application layer into one. And this is basically what it looks like, right? We have the OSI model on the left here. We have the DoD or the TCP/IP model on the right. So a lot of what goes on in the network we can look at from here. Most of the days, Well, most of the time when you and I are using the computer, we're using some one of these applications, something in the application layer space, be that is HTTP, SMB, something else. We're typically operating in the application space. Now, we will elaborate more on this shortly, but from a network communication perspective, everything in terms of your network, your normal protocol communicate or your normal communication is handled by your protocol stack, which has a protocol driver. Your protocol driver acts as the conduit between your network interface card and your network interface card drivers and your application layer. So we can say hook packets are the packets that traverse this protocol driver or this protocol stack, meaning that it goes through the encapsulation and the de-encapsulation process. In the next slide, we will quickly walk through the encapsulation and de-encapsulation process. But if you really want to get into the depths of this and how the different protocols work, come hang out with us at one of the SEC 503 class, and you definitely will gain more insights into this. So the other side is, if let's say the packets are traversing the protocol stack, we can consider those as cooked packets. For anything that is not traversing the protocol stack, let's consider those as raw packets. The raw packets is realistically what we want to see when we're capturing, and I'll explain why shortly. Most of the days when you're capturing, most of the days when you're performing packet capturing, you more than likely will be using, if you're on a Linux system, libpcap. Maybe if you are on an older Windows system, or maybe for compatibility or legacy issue, you might be using WinPcap on Windows. I think there's the newer NPCap, or I think it's NPCap it's called. But let's focus on libpcap here, right? Most of our capturing, be it you're using TShark, TCP dump, most of those tools, they use libpcap. And libpcap can operate in one out of two modes. It can do in-kernel filtering if it is leveraging BPF, that is Berkeley packet filters. And if it's not leveraging BPF, it will then copy those packets into user space and then do the filtering there. Now, from a BPF perspective, BPF has two components. And when I say BPF, we're talking about Berkeley packet filters. Has two components. One, there's a tap mechanism. And do note, both of these are software-based. I'm not speaking about a different hardware component that is outside of, let's say, the operating system or outside of libpcap. So we have the tap that is responsible for taking copies of the packet and presenting them to TShark. And we have the packet filter that ultimately decides on packets to be discarded or how much of that packet is to be presented to TShark. Now, if you're wondering about how much of this packet to be presented, part of it, by default, for example, when you're using tools like TShark or TCP dump and so on, there's a snapshot length that determines the amount of the packet or the number of bytes that is captured. By default, that value is more than likely 0, which means you're capturing the entire packet. But if for one reason or the other you decided, you know what, I will only capture the first 20 bytes or 30 bytes or 100 bytes, whatever it is, that is where the filtering mechanism will come into place to determine the amount of bytes to present to TShark or whatever tool you're using. In this case, specifically TShark. So here's the capturing process. So the packet comes off of the network interface card. Your driver picks it up, does the processing there. And your driver ultimately passes that, or your network interface card driver, I should say, ultimately passes that to your protocol driver, okay? Which in most cases, especially if you are on a Windows, it's going to be probably your TCP/IP sys or something like that. And this here is what is going to handle everything in terms of processing that packet so that it gets up to the application layer, which would be whatever process you're running in user mode. So if you think about it, right, this is where that encapsulation and de-encapsulation occur, where, let's say, the protocol, the packet comes in, it is identified as an Ethernet packet, the Ethernet header gets stripped, moves up to the IP layer, the IP header gets stripped, move up to the TCP layer, ultimately get into the application. Once again, if you really want to learn deeply about this, come hang out with us at the SEC 503 class where we go into greater depths on this. But what we focus on here today at this point is the BPF aspect of it. So what happens is these packets here are not traversing the protocol stack. So BPF gets a copy of those packets. And these raw packets basically is what we can now see in TShark. When I say that, that means we can see the entire Ethernet, IP, TCP, application layer payload, everything we can see via leveraging the BPF here. Otherwise, if we were using the protocol stack here, we probably would only see the application payload because of the application we're using. Think about your browser, right? When your browser says go to sans.org, you tell your browser to go to sans.org. You don't see when the browser adds the IP header and the TCP header and all of these things. But if you are to copy those raw packets using the BPF and presenting them to TShark, you'll see the entire Ethernet, IP, TCP application payload and everything. Now, once you start using TShark, you can either write to your console by default, or you can write to the file system, or you can manage a combination of both. Write to the file system whilst also presenting the contents to the screen. We will see some of that in the demo. So what is TShark? Packet analyzer, which capture packets of the network. When you think about tools like TShark, think about someone sniffing or eavesdropping on your conversation, someone listening while you're talking to someone else. Now, TShark is also the command line version of Wireshark, and in my opinion, it is much better for automating tasks. Supports Lua script. Later on, we will see in the demo where we use Python in combination with TShark to do the packet intelligence. But TShark, like any other application, runs in user space, right? And can write to standard output, a file, or both, and provides the raw packets as output. Those raw packets is what we can then analyze, be it we analyze them manually or we use some automated process, like once again, we will demo at the end of this session. So as I mentioned, sniffing, right, basically that is what TShark is doing, and most of the other tools that we use, basically they are eavesdropping. You're listening to the conversation on the wire. If someone is listening in on your telephone conversation, it's the same thing they're doing. They're sniffing your traffic, they're wiretapping. That is exactly what we're doing with TShark. We're passively listening for the communication as it crosses the wire. Now, TShark process what it sees, right? Let me rephrase that. Whatever comes in at the interface level and gets sent up to TShark, that is what exactly TShark will process. And on most days, your network interface card operates in non-promiscuous mode by default. What that means is, when your interface is operating in non-promiscuous mode, your network interface receives traffic. The traffic that is destined for your system will be passed up to you. Be it to the application layer or some other layer, that traffic will be passed up. Everything else will be filtered out. Now, if you are capturing packet, you want to see everything that your interface sees. So this is why now you have to transition your interface to promiscuous mode, where anything that is seen on that interface will ultimately be processed and be sent up to TShark based on whatever filtering mechanisms you put in place. Now, believe it or not, having your filters and being able to track promiscuous versus promiscuous mode in terms of your interface changes, be it via the Verilog message file or via dmessage or something like that, is important, because if threat actors manage to gain access to your environment and are able to load up a sniffer, then they also can capture those packets in your environment. And as you think about that, if you wish, you can research, I think it's Heartland Payments. Heartland Payments had posted, they got compromised, and in their let's say, post-incident report, it was mentioned that attackers actually gained access to the environment and did not really steal, let's say, steal data immediately. What they did is loaded up sniffers to sniff the packets off the wire. Okay. So once the interface transitions in and out from promiscuous mode, you should be able to see a message that says interface went into promiscuous mode. And you can now track that, be it via your SIEM or some other tool. So types of filters to be aware of. BPF filters, definitely probably one of the most used filtering mechanisms in place. When you're using TShark and you wish to use BPF filtering, you have to specify a -f argument. Can be used only in live mode. That means you can only use BPF in TShark if you're capturing live traffic. If you're trying to read back from a PCAP, you are unable to do that, as in TShark is going to report an error. Right? You can have filters that capture whatever traffic you deem interesting, right? Whatever you think is beneficial for you to be able to perform your packet threat intelligence, for example, right? And whereas we'll talk about display filters later on, your capture filter cannot really be modified while you're capturing, because if for you to modify it, you would have to stop the capturing process and restart it again. Your display filter, on the other hand, right, is a lot more interesting. You can do a lot more with display filters than you can do with capture filters. Can be used in live or readback mode. Specify the packets to be displayed, use selecting packets of interest, and can be changed on the fly. Now, this can be changed on the fly is not necessarily true when you're working with TShark, because TShark is command lines. So in order to change that, you have to once again stop the process and then modify the filter, then execute it again. But if you were using Wireshark, for example, then this would be no major concern. Now, we referenced capture filter, or we spoke about capture filter and display filter. It is critically important that you understand the difference between a capture filter and a display filter, because failure to clearly understand the two can lead you into a situation where you don't have the packets of interest if you wish. Now, think about it this way. When I set a capture filter, it means only that specific traffic must be captured, right? It means that if I say capture port 80 traffic and actually a compromise occurred on port 443, I will definitely not get that, get the 443 packets. In the case of Wireshark, if you have that display filter being used, the worst that is going to happen with a display filter is that you probably will have more packets than you anticipated. But setting the filter, you can always fix that in the end. But do note that capture filter is not as forgiving as display filters. Okay, so if there's anything you take away from this slide, note that I must be clear when setting my capture filters versus whereas with my display filters, providing that I have the correct interface that I'm capturing packet on, I can make mistakes and I can correct those mistakes later. But capture filter is not going to allow you to correct those mistakes later on. So risk associated with running TShark as root. Any tool you decide to run as root poses the potential for problems. Now, I haven't tested this with TShark directly, but I know with Wireshark, for example, you can use, for example, Metasploit, craft a packet that has malicious payload if you wish, and then when someone opens that PCAP file, right, you craft the packets, create the PCAP file, and provide that to someone. When they open that with a version of Wireshark that is vulnerable, an attacker can actually gain access to your environment via that packet that was created via Metasploit. So just be aware that if a compromise actually occurred like that, it means then that if that Wireshark or TShark, whatever it is, was running as root, automatically it's more than likely the attacker would have gained access to that environment as root. So be careful when you run these tools, be it as Wireshark, TShark, or some other tools. TShark does have the capability for you to specify that users can actually run Wireshark without being root, so you can take advantage of that also, or use sudo specifically. Now, I mentioned that from an interface perspective, your interface operates when you want to capture by default to transition to promiscuous mode. But if for some strange reason you did not want to capture in promiscuous mode, you would specify the no promiscuous mode option. In this case, I'm just saying TShark, and I specify the interface. I say EAT0. This interface could have been maybe ENS33, LO for loopback, something else. But I just specify here no promiscuous mode, meaning that I don't want to capture everything that I see. I just want to capture traffic that is destined for my host. Once again, this is just for information purposes. On most days, you more than likely will want to capture everything that is seen by your interface. So continuous hands-free capturing, TShark does have the capability for you to do continuous monitoring of packets. You can specify criterion such as maybe based on the file size, when it should stop capturing or when it should rotate files, maybe based on the duration, right? Do note though, when you use some of these here, if you don't have the right facilities in place, it can result in your disk filling up. Maybe you need to monitor your disk. Maybe you need to specify the size of the file so that it rotates appropriately. And we can use what is called the ring buffer facilities to overwrite old files. Basically, I can say, okay, create 10 files. And once you get to the 10th one, then just create an 11th one, but discard the first one if you wish. And then continue that cycle. So there's always going to be at most 10 files on your system, even though TShark probably would have processed hundreds of files if you wish. Now, when you're doing this, you also want to send that process to the background. And to do that, you more than likely use the ampersand, right? Because you don't want to have TShark running on the screen all the time. You want to be able also to maybe interact with that window or that terminal in some other way. So you just send that process to the background. Here are some arguments you can use. You can use the duration, right? Stop capturing after a specific time period, maybe the files. Stop capturing after the file reaches a certain number, maybe the file size. Stop capturing after a certain number of packets. Number of options available for you to ensure that you do not fill up your disk if you wish. So this is the ring buffer being used, for example, and this is why I call it hands-free, because once you set it up once, you don't really have to go back to it. So here we're saying create 10 files, right? We say TShark, we specify the interface, each 0. We say we want to use the ring buffer. File size, 1 kilobyte. In this case here, we specify that we want to write that output to a file. And what will happen is, even though I give it this base name, note I say base name, what will happen is TShark will now, after the key, add the date and the timestamp to this file. So I can then go back and I can see what is going on. Then I say once again, the ring buffer, and I specify that I want to have up to 10 files. And I use the ampersand to send that process to the background. So here's an example of some of those files that were created, right? We specify the TShark argument here, or TShark and the appropriate arguments. Then we see here a number of files were created. In this case, the files were created in the temp directory. This is by choice, right? Because I ran TShark here from the temp directory, and you can see all these files were created. We have file numbers, we have date and timestamp, and the PCAP file. Now, when you're capturing traffic also, you have to make decisions on whether or not you want to capture encrypted traffic or you just want to capture clear text traffic. Most of the world is moving more and more to encrypted communication, so this obviously will become a challenge. But it's not the end of the world, because there are decryption tools available for us to take advantage of that allows us to decrypt those packets, be it you take those packets and decrypt them on the fly, or you use some other mechanism. So here we're telling TShark, once again, we're using the ring buffer, but we're using a capture filter, note the -F. We're using a capture filter, and we say we want to capture traffic on TCP port 443 or 22 or 990 or 445, typically associated with encrypted communication. We have HTTPS, we have SSH, we have FTP.
Hey, Nick, I'm not hearing you right now. Nick, I'm not hearing you. Let's give him a minute to rejoin. Looks like he is offline for the moment. Thanks, everyone, for your patience. I know we've had a couple of issues with GoToWebinar this morning, so we'll just give him a moment. Thanks for your patience. Oh, it looks like he's back. I'm not hearing him, though. Maybe I need. All right, Nick is back with us. Welcome back, Nick.
Glad to be back. Technology at its best. All right, let me just share my screen again.
We do see.
Thanks everyone for the patience. Okay.
We're on continuous monitoring encrypted traffics, that slide.
All right. All right. All right, let me just continue going through here. So I was saying that I just finished the previous slide where we spoke about encrypted traffic, right? And then I was saying that, you know, instead you might just want to leverage clear text protocols in which you perform your packet capturing for. I mean, the reality is a lot of these protocols today are phased out or being phased out, I should say. HTTP, Telnet, SMTP, LDAP, most of these communications are moving into the encrypted format, or the encrypted traffic, if you wish, which makes it a little bit more complicated for our packet forensics or our packet intelligence and so on. So don't sweat it, as I say here. We have made it easy. We have a couple of scripts called packet intel scripts. The first script is what we use to check to see if TShark is running on the host, and if it's not, then we can just load up TShark to perform the packet capturing. And the second script is basically the packet intelligence, which goes and check your packets for information on IPs that might be considered malicious based on what vendors such as Cisco Talos Intelligence and them might have posted online. Right.
Hey, excuse me, Nick. I think I'm going to make you presenter again.
Okay.
I'm wondering if okay, let's have you reshare your screen. I think it was something listed as offline is what we were seeing, and the slides aren't changing. Sorry for that.
Okay.
So just go ahead and share your screen again.
Can you see it now?
Not yet. Oh yeah, now I do. Yep, and it's
okay.
Continuous monitoring encrypted traffic. That's the slide we're on, slide 22. Okay.
All right, thanks everyone for your patience. I'm not sure what the issue is there, but I will just go back through here. I was saying that ultimately we have to make a decision on encrypted versus clear text protocols, right? Some of the encrypted traffic you're going to see today, and a lot of these are used heavily in the network, HTTPS without a doubt. More and more of the communication we do on the internet is going via HTTPS. These days, it's very rare for you to find a site that runs on HTTP. For example, if you want to do that, you probably have to specifically look for that site. Clear text protocols, HTTP, Telnet, SMTP, LDAP, these are available today, but once again, I mean, I don't really expect anyone to be running Telnet in the network. And if you do, my suggestion would be you migrate from that and transition to something like SSH or even HTTPS, right? HTTP, once again, going the way of the dinosaur. Sooner or later, this is going to be a little bit more challenging for us to be able to monitor that type of traffic. But whilst it exists, we can still take advantage of it. SMTP, LDAP, you know, those protocols are still being used in the environment, and we can still gain intelligence from it or from them. So what I was saying was that don't sweat it. We've made it easy for you. We have what is called the packet intel scripts. Basically, there are two scripts. One is called check TShark. And what it does, it checks to see if TShark is installed in the system. And if it is, it's going to try to execute it. Obviously, it asks you first if you would like to run TShark. If you say yes, then we can start the continuous monitoring. And then we have the packet intel script that does IP, DNS, URL threat intelligence. Now, to be honest, when I first started this project, I was thinking, okay, the IP aspect of this is probably going to be the one that I get the most benefit from, right? And then I recognized, okay, IP and DNS as of today are the two that I will get the most from. Now, if you're wondering why I did not give DNS the same, I wasn't as curious that I might get the same amount of benefit from DNS. It is because these days we're talking about DNS over HTTPS, DNS over TLS, and so on. But even in the case of TLS or encrypted communication, some aspect of that communication is still in the clear text before it actually transitions to encrypted, to an encrypted format. So whilst it's in that unencrypted state, there's still intelligence we can get from that, and we will see some of that shortly. All right, let's take a quick demo. So for this demo, I will bring up Kali, right? And what this script is basically is a couple of scripts here, right? We'll see, right? Just these two scripts basically, okay? And we have a config file that is here. What this config file does is, because the script is these two scripts are reusing components like where you store your PCAPs or so on, we have the config file here. We have a file that has information on URLs that we can find malicious IPs, domains, as well as URLs if you wish, right? And if we take a look at some of these here, for example, we can see here, we can see information on malicious URLs. Similarly, we have malicious IP, or I should say suspicious, not necessarily malicious, but this is what the vendors post, and we're just trying to take advantage of that. So if there is a situation where there is false positives, well, we probably have to put some type of whitelist mechanism in place. But as it is, I'm trusting the vendors that what they produce is what is considered malicious at this point in time. So we have domains, we have URLs, some are HTTP, some are HTTPS, right? And this is basically the config file here. So let's take a look at the check TShark, right? Does some basic check, make sure the configuration is in place, and then it says here, you know, tells you about starting TShark. Basically, when it starts TShark, right? Start TShark. When it starts TShark, it basically starts TShark with these arguments, similarly to what you would have run at the command line. So here, I will just say check TShark, right? And it's going to check my permission, and it fails. Now, I need to run it either as root or as sudo, so I will say sudo, right? And we run it again. And if everything goes according to plan, then checking to see if TShark exists. So it looks like it found TShark. I will say yes. Okay, then we can see now that press Ctrl+C to exit. What's going to happen is it is going to write the PCAPs to this folder, the temp folder. Okay, and if I now say, let's say wget, actually, let's just say, yeah, wget sans.org. Okay, we can see here the packets are running on the screen as an example, whilst the PCAP would have also be written. Let me bring this up. The PCAP would also be written to the temp folder. So it is now, so today is the 5th. Let me just try this here. Grab 05. So we're looking for 2025. Today's at the 8th. So it's probably this file here. Okay, could check the date also. Yeah. Okay, this file here. So this is just the basic part of full packet capturing, right? So you can now take this script, put it in your environment. There's not much for you to do, and you now can see all of those packets and write those to the file. But whilst that is cool that you capture the packet, what really we're here for is being able to use this script here now, the packet intel script, to be able to gain intelligence on the IP addresses, domains, URLs, and so on. So let me go up here. Domain intel. Let me just find the IP intel. All right, we're looking for both IPv4 and IPv6 patterns in terms of the IP addresses. Okay, so this function here, right, is what takes care of a lot of the work around the IP intelligence. So what I will say now that we have those PCAPs, let's try this. Let's run the packet intel py, right? What will happen here, checks the permission. It doesn't need to be run as root, right? But you can see that obviously if your PCAPs were created as root, right, you will run into a problem in that you have to have root permission to read those PCAPs. We can see here it failed because you need to have either an IP, DNS, or URL option. Let's run this again and say IP. Okay. So as it goes through, it's going to ultimately go, and for every one of those IPs in the config file that we have here, the URL, okay, it's going to go out here and download all of those IP addresses that we're seeing. In this case, you can see 5,128 unique suspicious IPs were brought in. The reason I say unique is because I would have ensured I removed the duplicates and so on, so that there's no need to have that information in there. As the script goes through, it's going to run through the PCAP files, and in this case, you see it says it's looking to see if the SYN flag is set for those packets that are TCP. Now, you could have just checked if maybe the push and the ACK flag is set, which probably suggests, and this is more things you would learn about in the SEC 503 class. If you check to see if the push and the ACK flags are set, it's more than likely that maybe data is being passed. But in this case, I wanted to see when the communication was being initiated. This is why I check only the SYN flag. So it says, lucky you, nothing suspicious being reported at this time. But do note also, right, it also says it cannot read some of these files. So let's run this again. This time, let's ensure we are sudo, right? Because it would be quite interesting that, you know, all of these malicious IPs, out of 5,000 plus malicious IPs, and not one was detected in our environment. That would be super cool, super awesome if we don't have any threats in our environment. So it runs again, right? Notice it may take a while. It will go through, check those PCAPs. Right? Search through all the PCAPs. Here you can see in the script, right? We're running TShark again. We're checking the filter, right? If it's an IPv4 address, we are going to check to see, basically, we don't want to resolve the host name. Just show me the IP addresses. We read the PCAP file, all of those PCAP files in the temp folder, and we have the display filter here. We're checking to see if the TCP flags equals SYN, basically if that is set. And we don't want the SYN and the ACK flags to be set, right? We're not looking for communication that is coming back from the server. We're looking for communication that is initiated by the client. Similarly, we're checking UDP, we're checking ICMP packets, and then we're going to print out some fields. You will see what some of these fields looks like shortly, right? Print out some of these fields so that we can then get some insights into the information. In this specific case, we're just printing out the source IP and the source the source IP and the destination fields. Whilst that is performing, let me just go through something else. Ultimately, if we do find any threat, we'll write the information to what I call a session file, and this is where you see all of these different fields being presented. Because what is going on here now is, so initially, 5,128 unique suspicious IPs detected or downloaded, then 5 were found in our environment based on the PCAP files that we have. Right? So immediately you can see that you did not have to go to try to figure out what threats are there. This information now has already been taken out for you, and we can see it's being written to this PCAP file, to this text file, right? This text file here, information on the various sessions, and we will see the output of that shortly. One thing I want to do, and if you end up using the script and you think it would be beneficial, let me know. But what happened is that if you check in the conf section here, I have a section called mail, where my plan is to ultimately, maybe you put in your mail server address, and then I can use that to forward an email to you with the text file containing the threats that were found. This way, you don't really have to do anything other than just execute this process, maybe execute this script, maybe set it up as a cron job or something like that, that executes ever so often, maybe ensure it's running when the system loads, and then once you get that text file, you can then analyze it right there at your forensic workstation or at your desk, whatever it is that you do. So here we can see some files were created. So if I say ls, let's say all file with text. Let's take this file first, right? I will say cat. If I paste that file, we can see the IP addresses and the files in which they were found, right? So here you have these IPs and the PCAP file which they were found. So you can now go back and use that PCAP file to your benefit and decide to figure out exactly, or to learn as much intelligence or gather as much intelligence as you wish about the threats that has been seen relating to these IPs. And to make it a little bit easier for you, what I did also is, let's look back at these files here, and let's take the one with IPv4. I will say cat, and then I will pipe this into less, and let me here maximize this window, right? And what happens here now, you can see I'm writing even more information out to the file for you. So you now can say, okay, if I were to go back to that actual PCAP file, I know that frame 91, based on the PCAP file, frame 91, on May 8th at this date and time, this source IP, using this source port, communicating with this destination IP on this destination port, had a frame length of 76 and IP length of 60 bytes. So immediately you can probably use this and say, for example, why 573 here? I mean, 573 is not large enough to suggest something might be exfiltration, unless maybe the packets were being sent out in small chunks, or data was being sent out in small chunks. But at least you can look at this and you can say, yes, I do have some guidance here that I can build on. Similarly, let's run the script again, right? And this time, let's say DNS. Now, actually, before I run it for DNS, let me bring up something of interest here. Now, I said, right, that when it got to the DNS, I was a little bit concerned initially because of the DNS over TLS and all these things, or even a situation where someone might be going to an HTTPS website, but we did not manage to see that initial DNS request that led them to that site. So if we were to take a look at, let's say, TShark, let's say N, and we give TShark the file, in this case, let's say temp, and I say security Nik this here, and let's say 5, 1. Let's take this file here, right? We read this file here. Okay, doesn't have permission. Let's sudo. Okay, we have a set of packets here, but all of these packets don't interest us. What we're concerned about here is packets that we pertain information that might be suggesting something around encrypted communication on the web. And on most days, we know that encrypted communication on the web is done via port 443 more than likely. So I can put a display filter that says, let's say, let me put this in brackets, and I can say TCP.destination port equal 443. Why? Because I don't want to look at all the packets. I know that port 443 is typically associated with encrypted traffic via HTTPS. But even still, we have all of these packets here. All of these packets does not benefit me. You can see here, there's a client hello, right? So what I can instead do is say, okay, and build on this filter, I will say TLS.handshake equal 1. The 1 is the client handshake and the 2 is the server handshake. But I only want to see traffic that is from the client. So if I run this again, TLS.handshake type, sorry, handshake dot.
Nik, I'm not hearing you. Am I the only one who's not hearing Nik's audio? All right, thanks for all your feedback. We have lost Nik again. I will keep an eye out for him. I'm sure he'll rejoin. So let me just keep my eyes on him rejoining. Thanks again for your patience. All right, Nik is back. Nik, I need to make you presenter again. Hello.
Hello.
So Nik, you'll have to share your screen again. I just made you presenter. Thanks.
Yeah, let me know if you can see it now.
I'm not seeing it yet.
Can you see my screen?
Not yet. There we go.
So I have a message on my screen. Okay, good. My apologies, everyone. Technology at its best, so thanks for your patience. We're going to wrap up here shortly anyhow. So I was saying that, after all of these packets that we cycle through, we then filter that down by looking at only packets with the destination port of 443. And then we even filter that further by looking at only the packets that have, the client handshake set at 1, right? The handshake type. This is what, let me bring this back up, right? So we now have the client handshake type set at 1. So interestingly, you might be thinking at this point, 443, everything is encrypted. Most of it is encrypted. The majority of it is encrypted. But to get to that encryption state, at least with TLS1, up to TLS 1.2 and TLS 1.3 to some extent also, we can get what is called the server indication name, right? SNI, server name indication. So let's look at it this way. So if I say -v and I pipe this into less, what will happen here? Actually, let me just put it into more instead, because I don't need the entire thing. All right. What will happen here is if we look at this TLS packet, right, we have the client hello. And if we come down and we look at the extensions, right, we have extension name here, server name indication extension, and we can see the name here that the user was attempting to go to. So even though this traffic might be encrypted, ultimately, we are still able to gather information. So if someone were to, for example, click on a phishing link that is HTTPS, we can still see that the user went to this domain because of what we gathered there in the server name indication. So now that we know we have that, what we can do, let me clear the screen. I will now say, okay, show me this -t, and I will say fields, and I will say, show me the field. The -e specifies which field I would like to see, right? I say IP.source. Show me another field, TCP.src port, -e again, IP.destination, -e TCP.destination port. And I can say here now, -e TLS.handshake, SHAKE, dot extension server name. Okay. TLS handshake. Okay, let's see this here again. TLS extensions. Sorry, extensions. Okay. Now we can see that from that PCAP perspective, we have user at this source IP, this source port, this destination IP, this destination port went to this domain. So using that same concept, and for example, if I were to say, let's say here, DNS.query, I think it is name. Okay, all right, I don't have the exact syntax for this one, I can check the code. But if we use a similar concept to this here, when we run this script here, and we say DNS, we can literally get information on what is seen via the normal DNS request, as well as those situations where someone tried to connect via HTTPS, and we are able to see that server name indication, right? So in this example, the script goes out, download all that information via DNS, brings it in, it's going to ultimately aggregate it, try to do the deduplication, try to clean up, and so on. And in this example here, we can see over 175,000 malicious domains were downloaded via the script so far. And it says here, reading UDP TCP destination port 53. Now, in the SEC 503 class, for example, when we talk about DNS, one of the questions I like to ask is, what port does DNS use? And most of the, I'm sorry, not what port, what protocol does DNS use? And most times people say UDP, and they're right, but it also uses TCP. So this is why I'm tracking both UDP, TCP. If you want to know why when 53 is used, come hang out with us in 503 and we can talk more about it, right? But here we can see these 175,000 domains, suspicious domains downloaded. Here are the ones that were detected in your environment, or in this case, my environment, based on the lab. So what the script is going to do, it's going to go through all of these here, right? Go through all the PCAPs that you have and try to find this information so that it can, similarly to what we did with the previous script, where we did the IP, it is now going to tell you the source IP, source port, destination IP, destination port, basically all the information that makes it easier for you now as a forensic analyst to then go and say, hey, you know what? This host performed this activity on this date at this point in time. And you can then maybe correlate that with other activity to make your forensic analysis process or your network forensic process way more or way easier, I should say. This might take a couple of minutes. So what I can do, we can probably open another tab and just show the IP side of it also. I will say CD, packet intel, and I will say here, let's say sudo. Remember, it doesn't need to be run as root, and I'll say URL. All right, I'll say Kali. And similarly to what we saw for the IP and the DNS, it will basically go through the same process, right? So let me leave this here. It will basically go through the same process, and let me go back here. Go back here. This one is still, okay, this is still running. So whilst that is running, what I can instead do is, what I did in the meantime is I opened up that these scripts on GitHub. So if you wish, right, you can go on GitHub, grab it. Let me know what you think I can do differently. Let me know how, if there's something of interest that you think might be beneficial to you. As I said, I did not complete the part that has to do with emailing the results to whoever is running the tool. If you think that that might be beneficial to you, let me know. I can add the part where I just maybe say mail server is at this address, or you would put in your mail server. I would read that and I will send you an email with the attachments that contain malicious IPs, URLs, and/or domains that are found, if you find that beneficial. But let me leave this to run, and whilst that is occurring, we can probably take some questions in the meantime. But if you really want to learn more about TShark specifically and how we can use it as part of our network forensic analysis, come hang out with me at the upcoming SCC 582, the Mastering TShark Packet Analysis class. If you really want to get into the depths of the packet, really understanding how TShark or TCP dump or Snort or Zeek or any of those tools take advantage of packets, come hang out with us at the SCC 503 Intrusion Detection in Depth class. Or ultimately, if you, from a TShark perspective specifically, later on, you can grab a copy of my book, Mastering TShark Network Forensic, when it comes out. Hopefully that is probably sometime later on this month or early next month. But lots of opportunities we provide for you to learn about packets. As I said at the beginning, in the SEC 503 class, we say, show me the packets. Basically, packets, or it did not happen, right? And like I said at the beginning also, it doesn't matter what type of malware it is more than likely going to leave some type of trace on the network. And if it leaves trace on the network, providing that we are capturing those packets, we can gain the appropriate intelligence, be it we choose to do it manually or we choose to leverage the scripts that I shown here today and which are now available on GitHub for you to take advantage of if you so wish. So whilst this is running, Carol, we can probably take some questions if there are any. And when this is done, I will then just show what the file looks like, so everyone can get an idea of what the contents is. But it's going to be much similar to what was seen from the IP perspective, just that this is going to be related to DNS information. And do note also, whilst I did not show it, we are also capturing information from the HTTP host field. right? So it's not just the normal DNS or the TLS in this case, also information from the HTTP host field. All right, Carol, any questions there in the meantime whilst we wait on this here?
All right, thanks. Yeah, there's quite a few. Someone asks, what is a cooked packet?
All right, so what is a cooked packet? Well, on most days, when you're using your computer, you can consider all those packets that traverse your system as a packet that is cooked, meaning it is going through the processing process, it's going through the true process where the packet comes off or the packet is seen by your network interface card. Your network interface card driver does whatever it needs to do, and then that packet is passed on to the protocol driver. Let's say from a Windows perspective, that might be your TCP/IP sys or something like that. And then ultimately it gets to the application layer. But your protocol driver is also going to take care of things like the de-encapsulation and the encapsulation process, which is basically, okay, and as I said earlier, we elaborate on this a lot more in SEC 503. But this is basically from a de-encapsulation perspective. Let's say the packet comes off the wire. The packet now has to go through the process, right? It probably comes off the wire as an Ethernet packet. Ethernet has to understand, okay, the next header is actually IP. Then when it gets to IP, IP actually has to know the next header is TCP. Then when it gets to TCP, TCP actually has to know which application is waiting for that data, which means TCP might more than likely have a port that is listening on that. So think about it this way. When you wish to communicate with a web server, your system sets up a connection between your host and that web server, okay? And that socket established that full communication path. That process which that packet passed through to set up that entire connection is what we would consider the cooked packet. And in this case, it is operating through the normal path, as in going through the kernel and operating exactly as the system expected to. Now, if you contrast that with something like a raw packet, right? If you take SEC 503, for example, we talk about SCAPI and packet crafting. And actually, SANS will have a class coming up also focused specifically on SCAPI. When you use tools like SCAPI, you're crafting packets, which means those are not cooked packets, but raw packets. You're operating outside of the kernel, outside of the normal operations. Even if you use a tool such as Nmap, for example, you more than likely at times will be operating using raw packets because you'll be operating outside of the kernel too. Think about it. Actually, what I recommend is for the person that asks the question, run a TCP connect scan with Nmap and see how many packets actually occur or how many packets are actually seen on the network. On most days, when you perform activities on the network, you should have at least 3 packets as part of the TCP three-way handshake. And once again, we elaborate on this a lot more in the 503 class. You send your SYN act, and your final act. If you do the Nmap connect scan, for example, you might see a reset also included there, right? Which is a 4th packet, which is outside of the norm of what you should expect. So cooked versus raw. Cooked basically traverses your protocol stack, goes through normal processing, is handled by the kernel and so on. Raw operates outside of your kernel. Hopefully that helps.
All right, Nick, well, with that, we're out of time. I had put in the chat window that any questions not answered during this webcast can be submitted to q@sans.org. But wondering, do you have any contact information you'd like to put out there?
No, not really. I mean, you know, anyone can reach out to me, hit me up on LinkedIn, reach out to me, you know, send me a message. If you want to really come hang out with us at one of the SEC 503 class, we learn a lot more about packets, or come hang out with me at the upcoming SEC 502 class where we talk about mastering TShark for packet analysis. Right? But other than that, thanks everyone for hanging out with me. Hopefully you find the session beneficial. Feel free to grab the code from GitHub, and if you find it beneficial there too, send me an email. Let me know what I can do differently the next time.
All right, thank you so much, Nick, for your great presentation, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.